Hello guys, welcome back to Chris's Granite Paradise and episode 6 of our Common Yet Unique series dealing with rocks that can be found along the Yellowstone River. As promised in episode 5, where we talked about the volcanic rocks, today I'm going to be addressing porphyries, rocks of porphyritic textures that can be found along the Yellowstone River. We'll also be taking an aerial field trip, so stay tuned for that, overlooking some areas in the mountains that are of geologic interest. We'll also be referencing some other rocks from other areas just for comparison and contrast. So thanks for joining us. If you go online and look up the word porphyry, you are very likely to come across references to mining, to ore deposits, mining copper, gold, silver, and things of that nature. That is one aspect of the word, but for our purposes, we are simply talking about a rock. More specifically than a rock, we're talking about a texture. That basically means large crystals, and the word for these crystals is phenocryst, and they can really be of any mineral. It depends on what type of porphyry we're talking about. Most commonly they are feldspars forming in rhyolitic and basaltic magmas and everything in between, either below ground or on the surface. In this example, you can clearly see the larger white feldspar crystals. In this case, they're in kind of a floret pattern, which is known as flower stone. So while the subject of our video is mostly these volcanic rocks or rocks that are closely related to volcanism, by that I mean magma at shallow depths pushing up through the Earth's crust, or that has actually erupted onto the surface. These magmas come from great depths, okay, and the rocks that form at great depths, such as granites, I just put a few pieces here kind of as examples. Let's say we have granites on one side, which are a lighter color. If you trace up through the earth, that would give you your rhyolites and andesites and things of that nature. Your darker colored, heavier plutonic igneous rocks. And if you follow those darker ones, diorites, granodiorites, etc., up to the surface, you end up with these more basaltic porphyries. Basically, to boil it down to simple terms, porphyritic texture forms when conditions within the magma, usually because of movement up or changes in temperature or chemistry, can also create this porphyritic texture. So whether that movement happens between this layer and this layer, or whether that movement happens way down here between this layer and this layer, it'll create a porphyritic texture. And I'm going to show some samples here from the granite countertop industry. Of course, we did granite. We called it all granite, but it was many different kinds of plutonic igneous rocks. I'll show some samples here that also have a porphyritic texture. I think it's a good idea to go over very briefly rocks that are found in the Yellowstone that at first glance have a porphyritic appearance, in the sense that you may be thinking, well, a porphyry means a rock with chunks in it. And in the simplest terminology, that kind of is true. Let's look at some samples here. So these are amygdaloidal basalts. And if you watched, I believe it was episode 4, we talked about Montana agate. I know many of you are agate fans. Well, many of our Montana agates originate as vesicles in a basalt that later filled with agate. And these are some beautiful examples that were collected in Billings. But note, they are not a porphyry because these are agate-filled vesicles and not phenocrysts. Remember, the key word for it to be a porphyry is these must be crystals. Another rock that is common in the Yellowstone, we went over last time in episode 5 when we talked about the volcanic rocks, are these various types of volcanic breccias, whether they are basalt lava flows that have broken off and broken up a lot of chunks in them, or whether lahar deposits where there is volcanic mud flows and debris flows that later hardened. In both of these cases, and many other types of breccia. Here's I'm not sure what type of breccia this is, but breccias are composed of broken up rock rather than crystals. Again, the key word are those crystals. And we talked about rhyolites last time. Spherolytic rhyolite. Those of you into lapidary, you know that rhyolite very often has these unique spherical patterns, such as bird's eye rhyolite. But these spherules, on a microscopic level, are kind of radiating clusters of crystals. But they're not phenocrysts. So, while these at first glance look like they may be porphyritic, they are not either. I did manage to track down a piece of bird's eye rhyolite. I think this stuff is from Arizona. I really don't remember. But you can clearly see the spherical structure. And on the subject of these spherolytic rhyolites, there's a material called orbicular granite. And of course, granite is the plutonic version of rhyolite. It's the same general type of magma. And so orbicular granite may very well be the plutonic equivalent of this spherolytic rhyolite. If any of you know about this or have found orbicular granite in the Yellowstone, I would really like to know. If you could please let me know in the comments. And finally, I'll mention conglomerates, especially because in the Yellowstone River, the most common conglomerate that I find is this one with all black pebbles. We talked about this last time. It's kind of evidence of a paleo landscape where all the rocks were volcanic. And this sandstone, while it may have that appearance, but again, these are pebbles. They're not phenocrysts, so this would not be called a porphyry. The geese are flying over. We always love to see our geese. So before we go and start looking at individual porphyry varieties found in the Yellowstone, be it on the basaltic end or the rhyolitic end, and everything in between, I'll again use my sculpture as a whiteboard and go over some geology for you guys. So where do our porphyritic rocks in the Yellowstone originate? We talked briefly earlier about how down at great depths we have the plutonic igneous rocks such as granites, diorites, sienites, larvichites, any number of them that form at great depth. We're talking quite a few miles below the surface, maybe even further down, way down here. Okay, as far as we're concerned in the Yellowstone River, most of our porphyries originate in what we call dikes and sills, and maybe volcanic chimneys. For example, Devil's Tower is a classic volcanic chimney. That's not in the Yellowstone area, but it's an example that most of us know of. So how does this happen? So magma pushes up, forms a crack through the layers, and it may or may not reach the surface. The Beartooth Mountains, Absarokas, all the mountain ranges, and we're going to take an aerial tour here in a while and look at some of these dikes and sills. That's the wonder of Google Earth. But our mountains are riddled with these dikes and sills. A dike, if you can imagine, is a crack. You can imagine this is a sheet. It's not It's not just a hole punched through. It's a long front to back sheet of magma that pushes up, fills a crack, and hardens. So since this magma came from further down, moved up towards the surface, the conditions in the magma changed. You end up with these larger crystals in a finer matrix, and hence a porphyry. Another way this happens is the magma will come up and hit a layer that's too hard. And so it'll push along a weakness in those layers and fill the space. It'll either go a long distance and form what we call a sill, or it'll kind of form a bubble kind of deeper in the middle and then narrow, it tapers out towards the edges, and that would be called a lens. So we have dikes, sills, lenses, chimneys, all different ways that magma pushes up through these layers and gives us these porphyries. Let's take our aerial tour and look at some areas in our mountains nearby. I think you'll be amazed at the geology we can see. All right, everybody buckled in. We're going to leave here. We're here in Fort Collins, Colorado. I've already typed in the search Hurricane Mesa, Wyoming. That's where we're going. If we were driving, it would take quite a while. But on Google Earth, it's so nice. You just click search. Sit back. We get there pretty fast. There it is, beautiful Hurricane Mesa, one of the few flat-topped mountains in that area. I'll zoom out here so we can kind of know where we are. Where we're going to start our trip today is this wide overview. For reference, we have the Montana-Wyoming border, this white line. Right here is Cook City, Montana. If you're from Billings or you've been agate hunting much along Yellowstone, you're probably familiar with Highway 212 that goes from Laurel, goes up over the pass, over these mountains here. This is part of the Beartooths, and you can see that they are mostly made of granite. And you see how differently they weather. They're a lot lighter color, obviously, and they're more rounded. But as you come over, you get through Cook City, Silvergate, and into the park. But these mountains south of Cook City are all volcanic. There are sedimentary rocks under them, obviously, that can be seen along the highway in different places. But most of this upper portion is volcanic ash, volcanic scoria, a lot of softer materials. And remember, if you read the page I inserted from the USGS website, there have been many millions of years of various different kinds of volcanic activity starting long before the hotspot eruptions that we've all heard of. Most of us think of Yellowstone and we think of this giant volcanic eruption and that made everything there is. No, there were some 70 million years of volcanic activity, mostly in connection with what is known as the Laramide orogeny, which I won't go into it too in depth. That's outside of our scope, but basically it has to do with the plate tectonics and the oceanic plate. Rather than subducting at the coast, it actually slid under the continent way inland, even this far, and caused all this volcanism that you would normally see on the coast. Very interesting history that the scientists are still figuring out. It's still up for debate. I'll just touch on it to give you a little bit of background. But so over all those years, there has been a tremendous amount of erosion, various ice ages, etc. So these mountains are a small remnant of the volcanic landscape that once was. But if we look over this area, it is riddled with dikes and sills. Some of the mountains look like a spider web has been sewn over them, because you see all these white lines or little walls sticking up of different colors going every which way. And those are all dikes, chimneys, pipes, sills, etc. of mostly this basaltic and rhyolitic magma that may have or may not have made it to the surface. But what we're seeing today is the part that cooled underground. So let's zoom in here to a place called Hurricane Mesa. You can type in Hurricane Mesa in Wyoming, and Google Earth will bring you right to it. And it's one of the few flat-topped mountains in the area. This reddish area, I would imagine it's like brush and vegetation that's on top of this mesa. And I'm curious as to the geology, because it might be one of the original or the last remaining remnants of that original volcanic landscape before it all got changed by so much erosion. But this mountain has some very unique geology. If we zoom in a little further, you can start to see, for example, here's one right here. I hope they're showing on the video. Here's a bunch more down here. Dikes going different directions. They're kind of faint. I hope you're seeing them. Here are some more. We could zoom in a little bit here. There we go. Now they're starting to show up. And I realize some of this might be animal trails, but I don't think so. If you zoom in, they kind of cast a shadow. I've come across these before, walking through the woods and so forth, and they look like a little wall. They're however wide they are, maybe a few feet wide, maybe 10 feet wide, and they're harder rock than the surrounding volcanic material. Remember I said that most of this volcanic stuff is really soft. Scoria, breccias, cinder cone equivalent material. And so it erodes quickly, but these dikes are very hard. They're basalt, they're rhyolite, and most of them are porphyritic. And so they stick up like little walls all over the mountains. Okay, so that's one interesting thing I wanted to point out here. Let me try to back away. I'm going to try to turn us around. I think. Okay, sorry about that. I got a little off base maneuvering here, but now we're looking at the same mountain looking due south. So instead of looking back towards Cook City, we're looking further down into Wyoming. So here's the same slopes we were just looking at. And again, here are quite a few dikes and sills sticking out, just areas of hard rock. Some of this might be sedimentary, not sedimentary rock, but layers of volcanic deposits. But I don't think so, because they're going every which way. They're not necessarily parallel. But while we're here, and it's kind of unrelated to the video, but look at these. I'm not sure if they're debris flows, like from an earthquake and part of the mountain fell, or there might be a glacial remnant buried under these. I really don't know too much about the geology. I want to show it to you, though, because it's fascinating. Every one of these U-shaped valleys was probably originally carved by a glacier. But this one has one. Try to zoom in here. You can see how it looks like it flowed. Here are some trees to give you reference of the size we're talking about. Go over to the next little valley. Look at that beautiful flow. Again, that could be a sudden collapse event, or it might be a glacier that's still there. Those of you who are of a higher pay grade than me in terms of geology, you might be able to leave some comments. It would be appreciated if you know about these and what they actually are. To me, they look like almost a mud flow, like so much loose material, and it's gradually pushing its way down the mountain. I've said before that geology didn't happen in the past. Geology, as far as the earth processes, they're ongoing. So this right here is an example of, do you remember we looked at some volcanic breccias and lahar deposit rocks that look like basically concrete with chunks of basalt in them? This might be some of it in the making on the bottom of these flows. Very interesting. Go over to the next valley, and here's another one. This one's actually quite dynamic. You could really see the flow movement in there, and there's two of them. side by side. Here's one, and here's another one. This one, it would be interesting to hike up to this and stand at this leading edge, right at the tip of the tongue, as it were, and just see what's there. I'm imagining it's just broken up volcanic gravel of sorts, but it moves over time, evidently. And here in the wall, you can see more evidence of hard and soft areas, sills and dikes. Come over to this valley, and there's yet another one. This is all on the northern slope of Hurricane Mesa. See, here is Hurricane Mesa. And we're looking south right now. And so if you're curious about where those, for lack of a better term, I'm going to call them debris flows. They're all on the north face of Hurricane Mesa, which is south of Cook City, Montana. Anyway, thank you for joining me. Let's go ahead and go back to the backyard and continue looking at some awesome rocks. Here are a couple of beautiful porphyritic specimens that were collected in that area south of Cook City that we were seeing on our aerial tour. One is this beautiful, what appears to be a hornblende porphyry. The crystals are dark, they're very reflective. You can see if I move it in the sun, you might be able to catch the reflections. It's one of the few hornblende porphyries I have where the crystals are dark. And then this is a really nice example of another flower stone. And these probably eroded out of those dikes we were looking at from Google Earth. Okay, I hope you guys enjoyed that. That was a lot of fun. Let's go back to our little pile of specimens that we have out here in the yard. I want to start talking about our rhyolitic porphyries. These are perhaps the most common. And we'll start with, this is a specimen we were looking at earlier. These porphyries tend to be a lighter color as opposed to the more basaltic varieties. And the crystals are more blocky. It's just a different feldspar, a different chemistry. People who are far above my pay grade can look at these crystals and they can tell you whether they formed on the surface, whether they formed at depth. Because different conditions are required for the crystals to form in different ways. Here's another example. Keep in mind about our dikes and sills, there have been thousands of feet of volcanic activity erupted. One of the biggest events that actually pushed up the whole Beartooth mountain range and many other mountain ranges in the Rockies is an episode called the Laramide orogeny. And the Laramide orogeny is notorious for producing these dikes and sills through the rocks that it uplifted. To the point where these porphyries of this color and nature are actually called Laramide porphyries. I'm going to show you guys a piece from the Colorado River, very far away from the Yellowstone. I'll bring this piece over and we'll compare them. They're really very similar. So here we are back at my sculpture display of rocks from the Colorado River. These were collected mostly in the Durango area. I actually bought them from a landscape place here where I live, and they're beautiful rocks. But so here's the piece of Yellowstone Laramide porphyry. This was collected in Billings, and I just brought it over here and I set it on top of a piece I have from the Colorado River. You cannot tell them apart. If my rocks ever get mixed up, I'd have a hard time telling you which one of these came from the Colorado River and which one came from the Yellowstone. To me, they look exactly the same. So very interesting, our Laramide porphyries found in the Yellowstone River. So the laramide porphyry is not alone in terms of rhyolitic porphyries. The Yellowstone has many different types. One that is called andesite. Here you can see them sparkling in the sun beautifully. This has a lighter matrix overall, as you can see, but it also has these black needles, black little crystals of hornblende. There's a nice rectangular one there. See if I can get it to reflect. Andesite is typified by having both light-colored feldspar crystals and the presence of a few dark minerals, usually hornblende, pyroxene, things of that nature. Here's another variety, definitely more towards the pyroxene end, because the overall color is much greener, and those darker crystals are definitely green. This is a large andesitic porphyry. Here's my hand for reference. It's too big for me to pick up with one hand to show you the other side, but I cut it in half and polished it. I only partially polished it. We call it honed in the granite industry. But again, you can see the overall texture is porphyritic. Not a very exciting rock, but it's just cool to have it represented in the collection. This is a very common porphyry in the Yellowstone, especially if you go up Rock Creek towards Red Lodge. There's a lot of this porphyry there. In fact, I think this piece I collected in Red Lodge, right along the road there. But I've also found it plentiful in the Yellowstone. Another beautiful rhyolitic porphyry that I have, it's actually probably more correctly an andesite. You can clearly see all the black needles as well as the light-colored feldspar crystals. But what I wanted to show in this specimen is this beautiful, what is known as a xenolith, and that is a piece of country rock or local rock that the magma pushed through. Remember, we talked about the dikes and sills earlier. And so this magma breaks off inevitably pieces of the rock that it's pushing through. And this specimen, not only does it have this xenolith, but on the outside of it, and this is really cool, you can see the overall porphyritic texture of the rock. But this is where there was another xenolith. And of course, as it got eroded by the river, it eventually became weak enough that it popped out of there, and then the river continued eroding it a little bit, so it's polished smooth. But can you see the change in the texture of the rhyolitic magma where it immediately pressed against what was at that time the xenolith? You notice that the crystals are much smaller, and that implies that the rock was cool, and so the crystals are much smaller. And you can kind of see that along this one. You can see a slight color change. Again, someone far above my pay grade might be able to explain this better, but I just think this is a really neat specimen showing the xenolith in the rock and then where the xenolith was and the difference that it made in the crystallization of the magma. Moving along towards the more basaltic end of our porphyries. Again, in the Yellowstone, we have quite a few varieties. This almost looks like the matrix is almost pyroxene. It's very green. And then the feldspar crystals, almost the same color as the rest of the rock. If you look at this rock in the shade, in fact, let's do that. It really doesn't look like much. But when the sun hits it, you can see those large crystals reflect really nicely. It's a porphyry of some kind, definitely on the more basaltic side. But what I want to point out about our basaltic porphyries is the crystals tend to be more needle-like. As you can see in this specimen here, this is a classic example of more of a basaltic porphyry. Beautiful needles. Of course, we looked at this specimen earlier. Beautiful flower stone is the common term for this type of porphyry. And I think what happens here, you guys have seen it snow. On a calm day when the snowflakes aren't blown around by the wind, they tend to be much bigger and more beautifully formed. Well, I think the same happens with these crystals. If there's no movement in the magma, they have a chance to form these beautiful florets. And they're fairly common in the Yellowstone. Here's another one. Flower stone. That's a good name for it because they do kind of look like flowers. I'll insert some close-up pictures of some of these too. And of course, we cannot forget our beloved pudding stones. If you've collected along the Yellowstone River for any length of time, you've probably come across these. As you can see, I have a lot of them. And I mean, we don't pick up every one we find because they are common. I'm kind of picky now. the more you collect, the pickier you have to become. But my question about these pudding stones, I've included them here in the porphyries because they definitely have a porphyritic texture at first glance. And if any of you could help me, I would much appreciate it in the comments as far as the geology of these. I know they also occur in the dikes and sills. I actually came across myself a beautiful dike of pudding stone not far from Cook City. My brother and I were wandering out in the forest, and here's this wall. It looked like a literal wall sticking up. Not a man-made wall, but a dike of this beautiful pudding stone. But as I look at these, they don't really have a crystal form. They don't really reflect. I don't see any of the classic reflections that you would see in the feldspar crystals that I showed a minute ago when we were looking at the laramide porphyries. And no shape, no reflection. So if these are not crystals, they might be some kind of microcrystalline aggregates. Maybe they're quartz, maybe they're feldspar. I really don't know. So these might not technically be a porphyry. Again, I'm calling on someone far above my pay grade to clarify that question for me. There are some beautiful varieties. This is obviously a very attractive green color. But what I want to point out on this one, and you'll see this as you collect these, there's quite a variety. Most of them, the pieces are much harder than the matrix, and so you can see with the sunlight there, they protrude or stick out, whereas the matrix kind of erodes back. In this green one, it's a little different. The pieces are softer than the matrix, and so the matrix slightly protrudes, not by much, in this specimen. But you'll see that in our pudding stones. I like the big ones, and I want to give a special shout out to my friend Art for giving me both of these two very large specimens. They were both collected in the Yellowstone up near Columbus. And the story behind this one, his daughter was actually swimming in the river and found this underwater. So you might have to go underwater to find these really big ones. Well, thank you for joining us today on this overview of the porphyritic rocks found along the Yellowstone River. I hope you'll add some of these to your collection if you haven't already. As I've said before, the Yellowstone River is so much more than agates. Please like, share, and subscribe if you haven't already. God bless you guys. Always good spending time with you.